All right, so the next in the list of soft body vellum constraints are the struts. Struts are kind of in between super accurate simulation but relatively fast results. So this is why they're pretty handy to know. The difference to pressure is that they do not try to keep a volume intact. They're more like, three-dimensional connections, which we will see in a second. So this is made for everything that is, softish, but is not, you are not able to push air inside from, one side to the other, but more like, rubber or jelly or something like that. And it's not super physically accurate, so it's mostly made for relatively simple things. So if you type in struts, actually, you will find directly the Vellum struts, but be careful, just like with the pressure constraint and with the one we see next, the tetrahedrals, you actually need multiple nodes. And the base is still a cloth node first. So to make it a bit easier, I would recommend using the Vellum configure strut soft body, just like we saw with the configure pressure. And then you get two nodes for the outer shell and for the inner actual connection. And here you can actually see when you look at the result of the Vellum struts. And for a second, let's disconnect the cloth. We can actually see how they work, literally like struts. They're basically just lines, and let's quickly remesh our node. Yeah, so here you can see it better. They're literally just lines from one end of the surface to the other, trying to keep the volume intact. So this is the idea, relatively simple, and it also means again that they can't keep track of the overall volume. So it's good for simple stuff, again, like rubber. And if we try this and let it fall in a Vellum solver, of course, where we activate the ground, there you go, then it looks like this with the default settings. And you can see it's very similar to the pressure setup, relatively soft in the beginning. So let's increase the stiffness. And just like with the pressure, the weird thing here is there is no, strut stiffness or something. It's also called stretch stiffness because, side effects is reusing the interface, which makes it a bit confusing in my opinion. But before we look into that, have a look at the strut search, because this actually defines how the geometry is found. So there is a maximum length. So basically, when you put in a geometry, the constraint tries to find points that are on the opposite sides of the geometry. This is here, a safety net. So if your geometry is massive and longer than 100 meters, then it will stop trying to find those surfaces. So in the rare case that your geometry is much bigger than 100 meters, then you might have to increase that. But besides that, the settings are usually fine. Now let's increase the stiffness by 10 times and let's have a look at the result again. And it's still relatively soft, so let's go a bit further. Again, we want to try to make this look a little bit like rubber. So maybe 1,000. Yeah, and here you can start to see the idea. It becomes more and more rigid, but still soft. Yeah, a little bit like rubber. But you can also see a big problem. And that is actually what I wanted to show you. When we look at the geometry, we can see that there are like dents. So the whole thing becomes, crumbled. And that is because, the way you can imagine it, those struts are kind of pushing from the inside. And so this is why this weird deformation happens. This is simply an indicator that your substeps are too low. So this is not how it should look like. So you should probably increase the substeps maybe to 5, 10, 20 or 30 can also happen depending on your case. But let's try a lower number first. And what you will see, as we expect, the constraints will get stiffer the higher the substeps are. So don't be surprised that we might have to adjust our strut settings, our stiffness. And maybe let's try 10 substeps because it was still quite deforming, but the stiffness therefore can go down a little bit. So maybe to 1,000. Yeah, and here now you can see it's getting better. Of course, what we could have done as well is lowering the resolution like we played around with. Actually, we should have done that. So maybe something like that. Of course, we can still use the point deform later on to use the original geometry instead for rendering. Ignore the shading problem. This is easy to fix with the point deform. Yeah, and I think now it's better. Maybe it's a bit too stiff now, again, which is not surprising because we lowered the resolution. And you know the drill, whenever you change one thing, you have to change everything else. Yeah, so I think that's not too bad. And let's actually use a pointer form here. And then we can see the idea. The whole thing is supposed to feel like, it's soft, but it's still, it's not soft in a way that it's filled with some kind of gas or air, but it's, soft in itself. So this, again, can be helpful for, all kinds of stuff, rubber and so on, or jelly. And it's relatively fast to simulate compared with a one that is more accurate that we will look at in the next video, and that is tetrahedrals. So it's a good, in-between technique to get relatively fast, softish soft bodies. One example what you can do with this to not only work with the rubber toy is some kind of jelly here that I have. And I move it up a little bit so it can fall down, and then I use the Vellum struts. If we use the struts by default, it will probably not look great. So this is how the default looks like. Actually, it's not too bad. And this is another example what you can do with struts, and you can see it's pretty fast. In this case, I actually went away with just the default sub-steps. So this can work as well depending on your geometry, and you can see it even, wobbles away when my plate is moving back and forth. That said though, I want to be fair here. The struts are just one possible way of doing this. Just as a comparison, I did the same with the pressure approach, and this looks like this, for example, which is also not bad. So you don't have to necessarily, strictly follow what this is actually meant for. Definitely try different approaches and see where the results are best. And while I will not do this with the tetrahedrals, this is also possible to test with tetrahedrals. In this case, what I did is I made the cloth a bit more stiff than it was by default, and the vellum pressure is still on 1, but I made it also much stiffer so that it doesn't change the volume, and this is what we get out of it. So in this case, I would recommend the struts, because as you can see, the defaults already work quite well, but it's always worth trying the other soft bodies too. So yeah, that's the second soft body constraint type, struts. And keep in mind, they also work with two constraints. You have the outer surface in form of a normal cloth constraint, and the inner connection, which basically looks like, yeah, that's why it's called struts, like lines that connecting two opposite sides of a surface. And this is what keeps everything in shape. The advantage of this is, while not super accurate, it's relatively fast to simulate. So if you need something that is soft, but you don't need the idea of, volume that is preserving inside like a pressure would, but also you don't need the high accuracy of a tetrahedral simulation that we will look at next, the struts approach is a pretty good compromise between, complex behavior and relatively fast calculation time. So yeah, that's struts. I hope this is helpful. Thanks very much and see you later. Cheers.